suppose that I've got some fixed electric dipole, some distribution of charges where I have a charge plus q and a charge negative q, a fixed distance s apart. Now, if I put that in some external electric field, for ease of use in this case, I'm going to say that the electric field is constant, either because it's a large electric field or a small separation. These are both very, very useful approximations. And if I want to look at the forces acting on these, well, I know that the electric force is equal to the point charge times the electric field. So, let me replace that with a black dash line so that the red for forces will stand out. That means that the electric force on the positive particle will be, if I call this, I don't know, x, the x direction, the force, the electric force on this particle will be in the positive x direction, and the electric force on this particle will be in the negative x direction. Now, what this means, or what we're looking at, is that with the, if this is a fixed separation, what that's going to cause is that's going to cause that pair of charge to, it's going to cause that pair of charges to rotate. And it's going to exert a torque on them. That's one of the reasons why we had to cover torque in the previous semester as well. Now, torque, and again, for rotational motion, for a lot of these things, we're using Greek letters. We're doing that on purpose. We have a very limited numbers set of names to use. That's eta, that's not n. This is tau, it is not t. So tau is equal to the position vector from, and this is position vector from the point of rotation to where the force is being applied. And we take the vector product, or the cross product of that vector with the force vector. Now, in this case, the torque is equal to the vector, it's got a magnitude of s over 2 in the direction, well, it's the direction of s. But just for, we've defined p as the vector p is equal to q times the vector s. So let's say it's in the direction of p. Crossed onto the force, which is q times the electric field strength in the x direction. So, the torque is equal to 1/2 q times s, which is the magnitude of p from up here, times the electric field, times the sine of the angle between those two vectors. Now, that's just the torque on one particle. The torque on the other particle is going to be in the opposite direction in terms of x and y, but it's going to cause us to rotate in the same direction. This force would cause a clockwise rotation. This force will also cause a clockwise rotation. So the magnitude of the torque is 1/2 Pe times the sine of theta plus 1/2 Pe times the sine of theta. So 1/2 plus 1/2, or just 1, the vector P times the vector E times the sine of the angle between them, which I can write as the vector P crossed onto the vector E. Now, work, in its simplest definition, is the integral, or in its most complete definition, it's the integral of the force as it moves over some distance, which is up. Which means that it will also be equal to the opposite of the change in potential energy. Here, we are not going to look deeply into that, so I shall leave this as this stands.